Welcome! This is an explainer from the Sharif Center for Socio-Economic Systems Dynamics. We're about to tackle a really important jump in systems thinking, how we go from static maps that just show connections to dynamic models that can actually show us how a system behaves. We're going to see how these systems truly come alive over time. So, you know causal loop diagrams, right? They're a fantastic starting point. They really let you map out the wiring of a system. But they've got a big limitation. They're static. They're quiet. They can't tell you how the system is actually going to behave. To see that, to really watch it evolve or grow or maybe even collapse, we need a totally different kind of tool. And that brings us right to our first section, making that crucial move from a simple map to a full-blown dynamic model. So let's dig into why this step is so important. Okay, think of it like this. A causal loop diagram is kind of like a roadmap. It shows you that, yep, a road connects city A and city B. But it tells you nothing about the traffic, right? Nothing about the speed limit or where the bottlenecks are. For that, you need a dynamic model, something that can simulate the actual flow of cars and show you how they accumulate in a traffic jam. That's the difference. So what are these dynamic models made of? What are the building blocks? Let's break down the core components. This is the fundamental language of system dynamics. First up, we have the level, or what we more often call a stock. This is pretty much anything that can accumulate. It's a snapshot. It represents the state of the system at any single moment. Think about it. The population of a city, the amount of money in your bank account, the water in a reservoir. You can literally count or measure it at one point in time. Now, stocks don't just change on their own. They get changed by rates, which we also call flows. A rate is just the action that makes a stock go up or down. So going back to our examples, it's the births per year that change the population. It's the water flowing in or out that changes the reservoir level. It's the deposits and withdrawals that change your bank balance. Simply put, flows are what fill up and drain the stocks. And of course, the classic bathtub analogy makes this crystal clear. The amount of water sitting in the tub, that's your stock. That's the current state of things. The faucet is your inflow rate, and the drain is your outflow rate. And that water level is just a memory, isn't it? It's just the accumulation of all the water that's flowed in and out up to this point. All right, now that we've got the what, let's get into the how. To really see these parts in action, we're going to start with a super simple made-up system, one that has been specifically designed to have zero feedback. Welcome to the imaginary kingdom of Xanadu. As you can see from this diagram, its structure is about as simple as it gets. We've got a stock of population and only one inflow, births. And to keep it really simple, in Xanadu, nobody ever leaves or dies. The population only ever goes up. And here is the absolute key to this first model. The inflow rate is totally constant. It's what we call exogenous. There's a simple rule. Exactly 100 babies are born every year, period. It doesn't matter if the population is 5,000 or 5 million. The birth rate is completely independent of everything else. So how do we actually calculate the stock over time? Well, the logic is beautifully simple. The future population is just the population you have right now, plus whatever change happened during some time interval. It's just basic addition, really. So, if we put it all together for a Xanadu, we get this really simple equation. The new population is just the old population, plus the time step, let's say it's 1 year, times the number of births. And since births are always 100, the population just goes up by 100 people every single year. And check this out, the results are so clear. Look at the table. We start with 5,510 people, and the population just marches upward in a perfectly straight line. 5,610, 5,710, 5,810. It's totally predictable. The change is constant because the inflow is constant. This is what we call linear growth. Okay, but the real world is almost never that simple, right? So let's pivot to a more realistic example and see how just one tiny structural change can lead to a massive difference in behavior. Get ready, because this is the real aha moment. Here it is, the big transition. On the left, you've got that familiar reinforcing loop for population that we all know. And on the right, you see its stock and flow version. Now, the structure looks pretty similar to Xanadu, but there's one game-changing addition. See that little dotted information link? That link is everything. It tells the inflow rate what the current population is, and that allows the rate to change. So let's put them side by side. Xanadu's birth rate was just a fixed number, 100, but in our new, more realistic model, the net births are calculated by multiplying the current population by a growth fraction. Let's just say it's 2% a year. The rate is no longer fixed. It's now endogenous. It's part of the system. And that is the crucial shift. The rate of change now depends on the state of the system. More people means more births. It's a direct relationship. That little information link we saw, that's what closes the loop. It creates that powerful reinforcing feedback that we drew in the original causal loop diagram. Now look at this table. This is so different from Xanadu. The change in population isn't constant at all. It starts at a certain amount per year, but as the population stock gets bigger, so does the inflow of net births. The change itself is changing. This is the engine that drives nonlinear, exponential growth. So, what's the big takeaway here? What's the so what? It all comes down to the single most important idea in system dynamics. A system's structure is what drives its behavior. And this chart just makes that truth impossible to ignore. On one side, you have Xanadu's steady, predictable, linear growth. On the other, you have the world population's explosive, exponential growth. And what was the only difference between them? One tiny change in the structure. We just made the inflow rate depend on the stock. A tiny structural tweak created a profoundly different future. This really brings us back to the whole point of doing this. The source material puts it perfectly, saying the main reason we do this is to provide insight into the behavior a model generates. It's all about making those hidden dynamics, the consequences of how the system is wired, totally visible. So the takeaway couldn't be clearer. Getting a handle on a system's stocks, its flows, and its feedback loops, it's not just some academic thing. It's the absolute key to unlocking why a system behaves the way it does, and maybe, just maybe, how we can change it for the better. And that leaves us with one final thought to chew on. We just saw how one simple feedback loop completely changed a system's destiny. It really makes you wonder, doesn't it? What other hidden stocks and flows and feedback loops are secretly driving all the complex things we see in our economies, our societies, and our environment every single day?